3 problems only. One of the problem is irregular section, so pay attention, okay? Now, I have an irregular section, okay? So when I have an irregular section, I need to do a cutout, right? I have a cutout in the duct, right? So I need to put some HVAC in there. So the whole thing tells me that the compressive section is going to be here with a hole punctured in the middle, all right? So my job, first thing is to find a neutral axis, right? And then with the neutral axis, I can see the strain diagram, all right? And this is the compressive zone C here. And again, if I have some reinforcement, let's assume I have a chunk of reinforcement AS, then the depth of the beam is somewhere here, and the depth is called DS. And now all I have to assume is that epsilon S, which is strain of the group of the bars, would equal to Fy, the yield strain. So to solve this problem, right, all I have to do is, if I know C, right, and I can get my A, right? I can get my A, and now if I get my A, this is 0.85 F prime C, and then I can get the total compression force again, CC equal to 0.85 F prime C beta 1, and C, that's A basically, and B. And by the way, B is this width of the section here. Is that right? Is that right? Don't you feel weird? Something must be off. What is off here? There's an opening, right? There's a big chunk opening in the section, isn't it? And I haven't accounted for that, right? So to account for that, I say, folks, got to be careful. This must be so-called CC prime now. CC prime now means it is irregular. And I need to account for the opening. So it's like I am missing a 0.85 F prime C, then the area of the opening. The area of the hole. Okay, that's the part I'm missing. So for an irregular section, I need to consider that. All right, but that does not necessarily change the center of the total compression force. Okay, so that is still somewhere called A. And then all I need to do is find the distance between that A, half A basically here from top, and then to the level of reinforcement, and call this JD. And then I can get my moment, which is MM equal to AS Fy JD. So that is the process of solving a irregular section. Okay, so let's see, right? It's not hard, so let's take a look. So example number 1, I have an irregular section, right? And repeat, a nice rectangular section. And I have the opening somewhere here, and I have crossed it out. And I got my width of 16 inches. And I got my height of 24 inches. Okay, and then I have my concrete set to be F prime C of 4 KSI concrete, decent concrete, and yield strength of 60 KSI. Now, the problem is that if AS is given, okay, I need to find my MN, which is the nominal bending moment. Nominal bending moment. Okay, so here is that I want to turn this into a design problem because analysis for us right now is just too easy. Okay, so I want to see how I can design for this section. Okay, just like we did for a rectangular section, right? When we're not given the section size, we got this omega equal to beta 1 divided by 4, remember? So recall, somewhere omega equal to beta 1 divided by 4. But that was made under the assumption that epsilon t equal to what? Bling bling, remember? Epsilon t equal to what? 0.00 what? 7, 0.75, folks. Remember that? That's what we made assumption for rectangular section, 0.075. Okay, and that's how we derive an equation the omega equal to beta1 divided 4. Okay, but that is for rectangular section. So the difference between the rectangular section, let me put a mark here. This is for rectangular section. Okay. Difference between a rectangular section and an irregular section is that for irregular section, and when we do design, okay, we assume epsilon t equal to a 0.005. Epsilon t equal to 0.05. Okay, that is the big difference. Big difference. So starting from that point, things become easier. Why is that? Because I now can look at the strain diagram. I say, look, Bob, things couldn't be simpler. Epsilon Cu equal to 0.003. Okay, and I have certain height or the depth of, the actual compressive zone C, and I have a strain in the bars that epsilon t got equal to 0.005. So it is not so hard for me to get C equal to 0.003 divided by a 0.005 plus 0.03 and multiply by the depth of dt. And that gives me 3/8 of dt. This is all under assumption that still reached 0.005. Okay. Now with that, we also know that dt for a single layer reinforcement equal to h minus 2.5 inch. All right. Now h here is 24, which is given. The minus 2.5, I got about 21.5 inch of a depth. So with that, I can immediately get is C equal to 3/8 of 21.5 inch. But I can see that I didn't even bother to calculate A should equal to beta1 C for 4 KSI concrete. What is my beta1 value here? You just did the exam. For 4 KSI concrete, what is beta1, folks? 0.85. What happened? No coffee in the morning? Wake up, right? 0.85. And what is C here? 3/8 of 21.5 inch. So immediately I get my A, which is 6.85 inch. So at this point here, I get my A is 6.85 inch. That is the compressive zone. Now I have a dilemma. We just said in the beginning, right? It seems like the problem is simple. I get a whole compressive zone, substrate opening, right? I'm done. But you see, folks, this is done under one assumption is what? Is this a compressive area here cover the opening? Is that right? The compressive zone has to cover the opening. Opening has to be within the compressive zone, right? So let's check, right? And I didn't give you that information, so now I have it. And I know the opening is 2 inches apart from the top. Itself have 2 inches of height, and the width of that is 4 inches. So comparing the 6.85, I know this fellow here has to be greater than the 4 inch. So what I have is that the compressive zone, and to be precise, the effective compressive zone covers the opening. Okay, so that means I can treat it as a simple rectangular section with no opening. Okay, so from this moment on, things become quite easier. I say equilibrium tells me that I need a balance, right? So the equilibrium tells me that the compression force CC got equal to 0.85 F prime C. And now what is area underneath it? It has to be A and B, the width, but subtract the opening, right? And minus the area of the opening. Minus the area of opening. So this whole thing is so-called the compression force CC prime, okay, minus the opening, right? This fellow right here has to equal to what? the tension in the reinforcement, that is ASFY. Okay. All right, so let's take a look, right? So if I call it AC, meaning that is the effective compressive area, AC got to be equal to AB minus A opening, so equal to a 6.85 inch minus of 16 inches of width. Did I say 16? Yes, perfect. Minus a 2 inch of height of the opening, multiply a 4 inch of width of the opening. I got about 101.6 inch squared of area in terms of compression. So immediately, the AS reinforcement equal to CC prime divided by FY, so equal to a 0.85 F prime C multiplied by AC divided by FY, and bring the number in 0.85 multiplied by 4 KSI multiplied by 101.6 inch squared divided by yield strength of the bar 60 KSI. So I now know my reinforcement area has to equal to 5.76 inch squared. So that, ladies and gentlemen, is my first estimation of reinforcement needed for this irregular section. Just an estimation, right? It's not finalized yet. So with this, I say that if I have magical fingers, I can select any bars I want. And somewhere, somewhat, magically, let's just say I can provide, and I'm making life easier for us, so I can provide an accurate AS, which is unheard of in the field, but let's just say I can provide that to make our life easier for this problem. Then what happens? Now, if you can provide that, then your problem is actually solved, because now MN would just equal to what? Would just equal to CC multiplied by JD, which is the distance between the center of the compression and the tension of the bars. The tension of the bars. Okay, so here's a question. Can I do this now? MN equal to CC compression. Now, mind you, that's prime because irregular section. And can I do just the DS minus FA? Can I do that? We're all seasoned fellows now, right? Have survived the fire from the exam number 1. We know how to design a perfect rectangular section, right? So if it were a rectangular section, I would say this is perfect. Just proceed with that, right? But mind you that our opening is here. Can I do that? It's a simple question, yes or no. 50-50, it cannot be too wrong, right? Can I do that? Yes or no? I got a no. Do I get a yes? I get a yes. Wow, you're easy, fellow. Do I get a yes? Or do I get a no? So what is the promises, right? What is the promise I was given to utilize a DS minus half A? We need stress block, right? What does Whitney stress block say? It says that within my territory, we need stress block, right? Remind you, everyone, that the stress is uniform. Every point I see a 0.85 of F prime C, isn't it? Isn't it? That's the promise Whitney told us, right? And we took true, right? We hold true dearly, right? It's very nice. But for an irregular section, what's the difference here, folks? We have what? An opening, a hole, right? That means that the stress is not so uniformly distributed within the Whitney stress block zone, isn't it? So you cannot use this equation anymore for irregular section, and that's what we're going to test you in this exam number 2. Okay. So you say, Bob, if I cannot use that, what am I going to do? This is what we're going to do. Recognize the fact that, and now let me put an emphasis mark here. So recognize that AC, which is the compressive zone in the concrete, covers the opening.
Okay, I found this on the web for which is the compressor.
Yeah, sure, Siri. You know everything, right? But let me close you down.
I'm not sure I understand.
You're so smart. Okay, well, I'll just leave it alone. All right, so we recognize that AC covers open. So cannot use this equation anymore. Cannot. So instead, let's examine the cross section. Okay, so now I have an opening. I have the compressive zone like so. And I say, look, isn't this a superposition method? Isn't this a superposition method? Show of hands, how many of you have seen the superposition methods? A lot of you, right? In the static, you should have learned that. What is superposition method? That means one case can be decomposed into two cases added up together. So I say this case is kind of like a section with a solid section, no opening, right? Nothing in it. It's just beautiful rectangular section minus a opening only. All right, minus opening only. So if this is the case, I have two things going on. Mn essentially now should equal to compression, of course, multiplied JD, that's fine, but has two components. So from this rectangular section, I naturally have 0.85 F prime C A B, right? So this is A. Remind you that this is still A. The neutral axis stay the same, but 0.85 F prime C A B for the rectangular part, and the distance between the compression and tension, it is ds minus FA. No surprise. And this is my AS here. It is ds, okay? But now, I need to subtract this fellow here. All right, I need to subtract this fellow here. And that is minus 0.85 F prime C, okay? Minus 0.85 prime C, and area of the whole opening and multiply distance. And the distance now is what? This whole opening has a 2 inch of height. So I have 1 inch of distance right here. Isn't it? Now the ds is between the bars and the top of compression fiber. So the distance here, we call it JD2 equal to what? Equal to ds minus, right here, there's another 2 inch on the top and 1 inch right here. Is the distance from the top of the bar compressed fibers to the center of the block there, right? So here is ds minus 2 minus 1. Right? Basically the center of that opening, okay? So with this, I am set. Finally, I said, look, Bob, let me just use this equation. So 0.85 F prime C, and sorry, plugging the number in, 4 KSI here. Okay, A, what is A? 6.85 inch, we just calculated previously. And B is 16 inches. And the ds is 21.5. Everything's given. Now A, 6.85 again, divided by 2, happy, and minus 0.85 F prime C, and sorry about that, for KSI, opening of the hole, which is what? This is not AC, okay? The area is 2 inch by 4 inch, and then multiplied by distance 21.5 inch minus 3 inch. With that, I got my moment. And again, the moment Mn equal to a 519 kipfoot. Save you the agony of calculating. And I even can tell you, because I assume the phi, or sorry, I assume the epsilon t equal to 0.05. So what is my phi, folks? 0.9. And that's it. Is it hard? Is it hard? It's not hard at all, isn't it? Why it is so simple? Why it is so simple? I utilize the superposition. Why? I can use the superposition because what? The compressive zone cover the opening. So when I say this, is to say that this irregular section is the simplest irregular section you ever see. Nice opening in the compressive zone, take it out, done. Is that right? But in reality, it doesn't go like that. Okay, so in reality, that example number 2, I just want to show you this and we can stop here, is that I have a section like so. Okay, I have a section that has to have opening. Okay, so where did you see this from? From Disneyland. What? What? Where in Disneyland? Do you see castles? Right? That's a castle, isn't it? That's the guard, right? For me, I've seen this in the Great Wall, right? That's what it is, right? Do I need to draw a little figure here? Put a helmet here, right? Shooting arrows from there, right? Something like that, right? So we do have this type of section before, right? So now if I have that section, I say, look, folks, and make things worse, I need to have some opening to put my cannons over here too. Right, so top, I have a guy shooting arrows. Down there, I guess somebody fire the cannons, whatever, right? It's like acting the war, right? So now tell me, what is the capacity of this wall that when I lean on it? What is the bending moment of this section here? So how to solve this problem? And let me give you a dimension, right? It has a 4-inch of guard from left, 4-inch of guard from the right, have a depth of 2 inches for this quite opening. It's pretty shallow, right? And I have the same thing for the width of the opening, 4-inch right here. So this is 4 again. And then I have a opening of, I believe, 2-inch of a gap right here and 4-inch of width of the opening. So complicated. What are we gonna do? What are we gonna do? So when we see a complex situation, what we're gonna do? We play dumb, right? We assume it's simple first. See how complicated it can be. All right, so we kick it, right, to see how bad it is. So we start this whole business by assume the compressed zone AC covers opening. We just assume that. Okay, so how can we assume that? How do we assume that? Simple, right? So now tension force T equal to ASFY. You don't have to write this. We'll repeat this in the next lecture, okay? But I just want to give you a start. So tension equal to ASFY always, right? And let that equal to 0.8 F prime C, and say the total compressive area is AC. Make assumptions, right? Make assumptions. So now I can get AC equal to a ASFY divided by 0.85 F prime C. Then save you the agony. I got this number to be 70.6 inches squared. That is the total compression area I need to balance the tension force. Okay. Then I start to do this. I say, if I barely cover the opening, if my effective compressive zone, whatever you call it, A, right, covers the opening, right? So it should line up at the bottom here. If it line up, I'm fine, right? So let's assume this is assumed AC assumed, right? AC assumed is this red shaded area, right? So let me just do a quick calculation. So AC assumed equal to what? Equal to this 2 tiny block here. So 4 multiplied by 2 multiplied by 2 pieces, plus this tiny strip here, and the width I haven't given you, sorry about that, it's 12 inches. So 12 inches multiplied by a 2-inch of gap here, and multiplied by what? By 4-inch multiplied by 12-inch minus the opening. So 4-inch multiplied by 4-inch. Now, folks, needs your help real quick. I did not calculate this part. Can I get a number on this, please? Yes? Here? I think this is 4, And this is 4. Yeah, is that right? Maybe I drew it wrong. Let me see. No, I think I'm okay. It's 4 by 4. Sorry about that. Okay. That may confuse you, but can I get a help here? Can I get a number punched out from this? What do I get? So slow, man. 2272, right? Should I be happy? Bobby, you should be always happy, right? So my mom tells me that, but unfortunately, not all the time. Especially this time, I'm not particularly happy. Why is that? Why is that? Why is that? Because if I use my blue color, magical color here, indicating the boundary of my compressive zone, right? AC, isn't it? This line, folks, it's got to be somewhere here, isn't it? The most uncomfortable position ever. Barely covering the opening, but not quite. Now, can we use the previous nice method of block minus a block and be done with? We cannot. So the name of the game, and this is the last thought I want to leave you with, is I got this compressive zone size now, folks. And this compressive zone, as ugly as I don't want to admit, but it looks like this. Isn't it? That's the shape of the compressive zone now, isn't it? So I need to find out the what? The center of this compressive zone to get to the distance between the center and the tension bars and be done with. Right? And this is our favorite. Why this is our favorite? You've done this quite a bit in mechanics materials, and we call it, my dear friend, of moment of inertia. Remember? Moment of inertia. Trying to find the center, isn't it? Moment of inertia. That's the things we do best since we're high school, right? Okay. So that is the name of the game. Is to find the centroid of the compressive zone in the irregular section, the weird geometry. And that's what we're going to do for Wednesday. Okay. Alrighty, so that's it, folks, for today. Welcome to stay behind if any questions. And we'll talk about exam Wednesday. Make sure you show up, okay? Make sure you show up. And Wednesday, I'll make a quiz. There will be a quiz, in-class quiz on Wednesday. So let your friends know they better show up, okay? So I keep attendance. All right, thank you. And see you on Wednesday. All right, folks, appreciate that. Sarah, Audrey, are you guys okay?
Yes, thank you.
No problem.
Yeah.
So I'm going to put this on the YouTube, all right, Audrey and Sarah. You can find the links from the canvas and file folder, okay?
Okay.
Sounds good.
All right, see you guys later. Bye now.
Bye.